Welcome to the first workshop on quantum and statistical physics. We are very happy for your effort to come here and share the rest of the week with us. We hope every one of you has a good time to discuss your research topic. Maybe this will inspire you with new ideas to new projects and maybe collaborations. I would like to do a fast passing through the programming of our event. We try to organize the talks by topic. Obviously, all of us has lots of responsibilities, so we were not able to put every topic together because we have to adjust depending on the necessities of the speakers. But we have a first day focused on quantum mechanics, simulation techniques, and analytical works. The second day will be focused on statistical physics. And the third day, we will have some more quantum mechanics. And by the end of our meeting, we are going to have talks from Andrea Paza and from Rolando Felix about experimental results. So I would like to invite the director of the Institute of Physics of UNB, Professor Olavo. And I would also like to invite the director of the Institute of Physics, the International Center of Physics, Alexandre Dodonov. I would like to acknowledge the financial support from FAPDF, from SBF, and from the Institute of Physics, and all the logistic support too, with the organization of the event. Now I'm going to pass the word to the director of the Institute, Alexandre Dodonov.
First is Olavo, actually. Okay. It's more important.
Well, thank you all for being here with us. It's very important for us to have you here communicating your works and passing your knowledge to everyone. I'm very happy to be here in this opening table to stress once more the relevance and importance of this kind of events for our institute. This is my part of the job, to stress the relevance for us, the Institute of Physics. Not only because this is a moment to exchange ideas and to make the institute idea-driven, but also to make a web of relationships that can improve our connection to the world and go outside our walls in the institute. So I'm very happy to have this kind of event with Professor Dodonov. We changed very much the appearance of the CIF, our, how can I say, ICP, our ICP, which was not very productive in some years before, but now it is very productive and is being able to put forward a lot of events, important events, some international, some national events. And I would like to stress the importance of the presence of our professor, teachers of the Institute, of our students, postgraduate students mainly, and to hope that in the future we can make here also schools, small schools that make our students, if they can come, to put their hands to work. I think it's very important to have what I would call workshop. Strictly speaking, an opportunity that our professor, our speakers, will have to call the students and to make they work indeed in their areas of research, to put their hands in the work itself and not only in presentations. Presentations are very important. They make their points and with respect to the way knowledge can flow within us. But I think it's also important, and this is some way of speaking, something that I will kindly ask the ICP to. I'm listening myself with delay. And so I would like to thank you again for coming to this event. I think it will be a very nice event, a lot of different themes will be being presented here. So thank you again and have a nice event. Thank you.
Okay, thank you all for coming here. I'm just going to describe briefly the idea of this workshop and the activities of CIF or ICP as we do here. So I just make a very brief presentation about the history of this workshop. But you're going to ask, how about the history? Because it's the first ICP workshop on quantum and statistical physics. Actually, it's kind of first, but it's also fourth workshop. And I'm going to explain why. So this is a workshop of ICP, the International Center of Physics. But in the past, it was other name. It was the International Center for Condensed Matter Physics, and it also had plenty of events. So just recalling the history of the ICP and ICC MP. So we had 1, 2, 3, 4, 5, I think 5 or 6 directors beginning in 1988. And I'm very happy that in this current workshop, we have presence of 83.3 of former directors of ICP and ICC MP, either as speakers or in the audience. Because as speakers, we'll have Professor Fernando, Marciano, and Victor. And in the audience, we'll have Professor Hugo Nazareno. So just recalling the history of ICCMP, so as far as I could find in the internet, the first director was Álvaro Ferraz Filho. And then in 2022, the center changed its name. It became simply ICP. So from 2022 to present date, the director is A229, whatever it means. I have no idea. And about the history. So the second workshop on statistical physics occurred in 2015. I found this file in my recycle bin, so I realized I haven't been emptying my recycle bin for the last 10 or 15 years, but it's very nice. So we see that in this conference, we also had plenty of talks about statistical physics and also quantum physics, and we have a lot of attendees that are also here today, like Professor Tarcísio Marciano. Aníbal is also here. Even I participated in that workshop. And it was very nice because we celebrated the 80 years of Professor Hugo Nazareno, which will be here also as attendee in the next days. And also Fernando was at this conference. And just to mention that we have, although the name was statistical physics, we had presentations on several fields of quantum physics and other topics. And then we had the third workshop on statistical physics in 2016. And actually the organizers were me, Fernando, and Tarcísio. And I also noticed some very important and interesting fact about that workshop, because it was in 2016. And the round table was about epidemic propagation. So it shows how the activities we do here at CIF predict the future 4 years before. So we had talk on 12th of May, then 12th of June, then, it's December 5, December 6, and December 7. So it's English notation. And the idea of ICP workshop, this, which actually is the first edition, but in some sense is the fourth edition, is because of this little file here, because one of the most important parts of the workshop are actually not the talks, but what we call the quantum happy hour. So every day we're going to have a quantum happy hour at some bars, and this is the most important part of the event. It's where the ideas and new theories come up. But just to let you know that everyone pays its part in the bar, so it's not part of the program. So today, tomorrow, and on Friday, you are all invited to go to the bar with us to discuss quantum gravitation and all the stuff nobody solved till now, but perhaps we solved now, as was the case of the epidemic propagation back in 2016. And just briefly about the forthcoming events at CIF. So we have the colloquia of CIF, and one of the colloquia will be presented by Professor Andrea Avelino Pazza this Friday, which will end this workshop. And we also have 3 more confirmed events for this semester, but the dates are still in open because of the strike. But in principle, we have these 3 colloquia this semester, and also more 5 or 6 colloquia in the second semester. And other forthcoming events is the 3rd International Workshop on Quantum Non-Stationary Systems to occur in August, and also the JOCAF, which will be the first event with hands-on on quantum technologies and artificial intelligence, which will be carried here at CIF during the Semana Universitaria, roughly in the fall of this year. Okay, so that's about it was a brief remark about the activities of CIF for the forthcoming events. I thank the Professor Olavo Ismael for organizing this event. If you don't know, the website of the event was done by Professor Olavo in his free time. So when he is not doing physics, he is doing PhD in philosophy, a lot of other PhDs, making web pages and so on. So now we're a bit late on time, so we proceed already with the first talk of this conference. So I am very happy to invite Professor Mariana Mallard to give the first talk of the workshop, and I thank again the other organizers, Olavo and Ismael. So now, so please, Mariana, you are the first speaker, and it's an honor to have you here.
Good morning. Hi, everyone. Thank you for being here and making an effort to be here with us. I will not thank the organizing committee because I'm part of it, but I'm very glad that we were able to put together this nice workshop with a good attendance. And we are, as you know, we are in the middle of a strike, so this made it a bit more challenging than it would have been otherwise. So I'm very grateful that we are all here this morning and through the rest of the week. So I'll talk about some setups for synthesizing, detecting, and leaking Majorana-bound states. So without further delay, let me begin. So first, I would like to make just a very brief introduction about the Kitaev chain, which is a toy model for topological superconductivity, which is particularly aimed to showing that it's possible to realize Majorana particle in condensed matter physics. But before that, let me just mention that Majorana particles were predicted already 86 years ago by Ettore Majorana. And these are very interesting particles in the sense that they are fermions, which are their own antifermions, which is represented by this equality here. So, these particles, as free particles in in free space, haven't been observed or measured yet. And by the way, if you're interested in a little bit of history of physics, Ettore Majorana himself hasn't been observed since 1938 when he went missing. And this is a little, it's a bit interesting. So, okay, so 23 years ago, Kitaev put together this very, very simple toy model, which is a one-dimensional chain of fermions. And it's shown very straightforwardly that each one of these fermions can be decomposed as a pair of Majorana particles along this chain. And this is the Hamiltonian in the fermionic language. So it has hopping, chemical potential, and a superconducting pairing between the fermions. And this is a realization of a one-dimensional topological superconductor where for certain regime of parameters, you will find decoupled Majoranas at the end of this chain. And so one thing that has to be, one condition that has to be obeyed is that the hopping amplitude must equate the superconducting pairing amplitude. And in this case, you can view the chain as just a chain of Majorana particles. And there are two interesting disconnected dimers regime. One is when T equals 0. So you just have this Majoranas bound by chemical potential links. And this is a realization of just a trivial insulator. Remember that each one of gamma 1, gamma 2 forms one fermion, gamma 3, gamma 4 forms one fermion. So then you just have this disconnected fermions on a lattice, which is just some simple, the simplest realization of an insulator. But if you now turn off mu, which is the yellow links, what happens is now you have this unpaired Majoranas at the end of the chain, and it turns out that this realization is a topological superconductor. And the interesting thing is that this phase of the model, it's not realized only when mu equals 0, but as long as it's smaller than the double of the hopping amplitude. And the reason for that is that this phase is topologically protected. And how do we know that? We compute something that it's called a topological invariant, which for this kind of model is a winding number, and it comes out of this Hamiltonian, which is the Hamiltonian of the fermionic version of the Kitaev chain. So it's just a 2x2 matrix. These functions are known in terms of the parameters of the model. And then if you just compute the winding of this vector, which is formed by this epsilon and delta functions on a plane, as k swipes the Brillouin zone from -pi to pi, you realize that this winding of this vector, it may or may not enclose the origin of the plane depending on mu, and T, so depending on the relation between the chemical potential and the hopping amplitude. So this is the apex of this loop. So when mu is larger than 2T, so this apex is below the origin, so this loop does not enclose the origin, but otherwise it does, passing through a condition in which the winding number is undefined exactly when these two quantities are equal. So then we have something which is called the bulk boundary correspondence theorem, which guarantees that if the winding number is 0, then you have no topological edge states in your model, which is for this particular class of model, is a realization of a trivial superconductor. Otherwise, in this case, this y in the number equals 1, so which is a guarantee that you're gonna end up with one topological edge state at each end of your one-dimensional lattice. In this case, these are going to be Majorana edge states, and therefore you have realized a topological superconductor. Okay, but this seems to be all very theoretical and even kind of just some algebraic trick, because it all relies on the decomposition of a fermion operator as two Majorana operators. But is there some reality to this thing? So why are we so obsessed about really detecting and realizing these Majorana bound states in condensed matter physics? Well, first of all, there is a fundamental interest in this pursuit, because we want to know if there are self-annihilating particles in nature or not. Maybe they will not be found anytime soon as free particles in empty space, but if we are able to realize them or cook them up as emergent excitations in condensed matter physics, that would be very, very interesting for fundamental physics. And there are lots of consequences depending on the answer to this question. But also there are very important technological implications. And I'm going to cite just one of them, which has to do with our ability to actually build a quantum computer that actually works in a desired way, in that it's low decoherence, fault tolerant. In this case, it would be based on braiding Majorana excitations in this device. Because, by the way, Majoranas in condensed matter, they're actually not fermions. They follow non-abelian statistics. In this case, this means that braiding this excitation, you can generate all kinds of interesting phenomena for quantum computing. So now I'm just going to very briefly pass through some proposals. This is obviously not an exhaustive list, but some important prototypical proposals for probing or realizing Majorana states in condensed matter. So starting in 2008, Fu and Kane proposed that combining topological insulator with a normal superconductor, a topological superconductor could arise. Around 2010, several proposals involving cold atoms were put forward. Also, this very one proposal, which has become very prominent in the field, which involves a semiconducting wire with spin orbit coupling, normal superconductor, and magnetic field. Quantum dots with superconductor associated to them were also investigated, magnetic atoms plus superconductor, and many other instances. Talking about this 2010 scheme, in 2012, the zero bias conductance peak, which had been considered as a signature of Majorana bound states in such realizations, were measured by these guys. And there is a very rich story, I could say, or history, I don't know, in this related to the zero bias conductance peak, including dramatic paper withdrawals. So if you're interested, you could check it out on the internet. But the conclusion is that the zero bias conductance peak is not a unique signature of Majorana states in condensed matter systems. Many other excitations could lead to such a signature in the conductance. So we, in 2016, my co-workers and myself have come out with some interesting idea, I think, which is to, some of the problems with this kind of realization is the magnetic field. I will not go into the technical details or even the theoretical details why the magnetic field has some drawbacks, but well, just believe me that if you would be able to have some realization that does without the magnetic field, that's desirable. So we ask the question, is it possible to replace the magnetic field with a sequence of electric gates that would produce a modulated electric field, and would this replacement lead to topological superconductivity? So we studied this proposal. And well, here is just the microscopic model that describes such a scheme. So as you can see, there's the usual free Hamiltonian that includes hopping, chemical potential, and in this case, we have to include two types of spin-orbit interaction, Rashba and Dresselhaus. And the important point here is that this modulated electric field will induce modulation in the Rashba spin-orbit coupling, because this type of spin-orbit coupling is sensitive to electric field. So this is the modulated part of the spin-orbit coupling. Q here is the wavelength. The inverse wavelength of the modulation is the wave number of the modulation. Of course, the chemical potential, it's not important, but it will also be modulated by the electric field. So we include the modulated part of the chemical potential here, same wave number. And then we have just regular S-wave normal superconducting pairing, delta, and electron-electron interactions, which are important for the physics that we want to convey. So before we analyze the simpler version of that scheme without the superconductor. So in this realization, we don't have delta, or delta equals 0. What we found is that, first of all, because you have spin-orbit coupling, you have two spin-split bands, one for spin up, the other one for spin down. And then as you introduce the modulated terms due to this applied electric field, first, something that not trivial happens is that instead of two bands, now you have some multi-band model depending on the wavelengths of, on the wave number of this modulation, because now your Brillouin zone, which went from -pi to pi, now goes from -pi over some number, which is actually Q, and plus pi over that number. So here I'm just assuming 3, but could be any other number. And then you have just this multi-band model in a shrunk Brillouin zone. But that's just, I mean, there is nothing interesting in it by itself. But in this Hamiltonian, we also have some modulated spin-flipping terms, which come from the interplay of the Dresselhaus, which is uniform, and modulated Rashba. And the reason for that is that they don't have just one spin quantization axis anymore, because these two spin orbit couplings are orthogonal. And then this generates some spin flipping processes in your Hamiltonian, which in this case, when assisted by strong enough but not too strong, I'll come to that, electron-electron interactions, open a gap at the boundaries of the Brillouin zone of the lower set of bands here. Why is this so important or relevant? That it's irrelevant, it's relevant because now if your Fermi level is exactly cutting through this gap, which is opened at the edges of the Brillouin zone, what's left inside at the Fermi level is spinless states, effectively, because now they spin up or down are locked to the direction of motion, so it's not a degree of freedom. So you end up realizing a spinless fermions in one dimension. This is a one-dimensional model, which is the basic ingredient of the Kitaev chain. So this is a good starting point for Majoranas, and just observe that this selective gap opening at the edges of the Brillouin zone, but not inside the Brillouin zone, happens is just at the Fermi points, which are separated by the wave number of the external modulation. This is because only the excitations around these points are sensitive to this physics here, and not the excitations inside, which are not separated by Q. They are kind of blind to this physics here. Okay, so now the question is, can we actually expect topological superconductivity arising if we now bring in the normal superconductor into the game? And well, to answer this question, we have to address the fact that first, there will be competition between superconductivity and spin-orbit coupling, spin-flipping processes around the edge Fermi points, the Fermi points at the edge of the Brillouin zone, which I'm calling outer Fermi points. And also because there are electron-electron interactions, there is actually coupling between whatever happens here and here and here and here. And this has to be properly taken into account if we are serious about claiming that topological superconductor is actually robust in this framework. So to do that, to answer this question, we have to recast the Hamiltonian in a low energy and bosonized version of the microscopic Hamiltonian. With skipping all the lengthy details, we end up with a Hamiltonian that's split in 3 parts. One that describes the physics at the outer Fermi points, inner Fermi points, and this part which mixes outer and inner Fermi points. And what you're seeing here is just a bunch of sine-Gordon potentials. In the outer branch, we have these 2 sine-Gordon-like potentials. In the inner branch, just this one. And then what you see that in the outer branch, you have competition between superconductivity and the spin-flipping processes, both of which are governed by the Luttinger parameter K. K here is a parameter that is proportional to the intensity of electron-electron interactions in your one-dimensional system of electrons. And in the inner branch, I just have normal superconductivity also renormalized by K. Okay, so I carry out what is called the renormalization group treatment of this Hamiltonian, and I end up with some renormalization group flow equations for new dimensionless parameters, which are defined in terms of the previous ones. So this is electron-electron interaction, spin-orbit coupling, proportional to lambda squared, superconductivity, proportional to delta. And these are the flow equations. And then if you just solve this set of coupled differential equations, you get what's called the flow of these parameters in the parameter space. And we get something that looks like this. This is a critical plane. And what's important to understand is that above the critical plane, the spin-orbit coupling is strongly or at least marginally relevant, strongly in this, for this choice of initial conditions, marginally relevant for some other choice of initial conditions, but which means that whatever was happening at the outer branch continues even in the presence of superconductivity, which in this regime is irrelevant. It's washed out from the outer branch, basically, at the outer Fermi points. So this is a good house for Majoranas, which means that I am able to keep the outer branch gapped out and just turn superconductivity in the inner branch, where you have this effectively spinless fermions living there. But below the critical plane, the situation is reversed. Now it's spin-orbit coupling, which becomes irrelevant, and superconductivity is marginally or even strongly relevant, which means that this is no good for Majorana, very inhospitable for Majoranas, because the outer branch is in the game again, and it mixes up everything, and you cannot claim spinless and many other necessary conditions. So just briefly depicting the phase diagram that comes out of the renormalization group for some fixed value of the spin-orbit coupling on the superconducting pairing electron-electron interaction plane, you have two critical lines. Below the lower critical line, you just have helical liquid at the outer in the system, because superconductivity is so weak that it's washed out from the outer branch, from the inner branch, and you just back to the helical liquid that you had before. Above this critical line, you have, it's so strong, superconductivity so strong that it opens a superconducting gap all through the whole Fermi level, and you end up with just a regular superconductor, S-wave type. And in the middle, you have this compromise in which you keep the outer branch gapped out, and in the inner branch, you realize a P-wave type superconducting pairing, which is the spinless type of superconducting pairing, which is the realization of a topological superconductor. I will not talk about this gray region here. It's more complicated, because in this region we cannot claim decoupling between outer and inner branches, and it's more complicated. So, of course, the experimental regime will not be that large, right? So it will be some subset of the blue area here. And in the paper, if you're interested, we do carry out two case studies, one for a cold atom realization of this model, and another one for a more standard solid state nanowire realization with the proximatized superconductor and applied electric field that looks like the cartoon that I showed you. And we actually found that even with experimentally meaningful parameters, there will be some region here where this model could be realized, and therefore a topological, one-dimensional topological superconductor without magnetic field could be achieved with edge Majorana states. Okay, so with that, I come to the conclusions of the first part of my talk. So basically, we are able to produce a model for Majorana zero modes with zero magnetic field, which relies on a competition between normal superconductivity and a helical Luttinger liquid with electron-electron interactions. Helical means spinless in this context. So the competition between these correlations and superconductivity gives you this regime of topological superconductivity in this model. Now, how am I doing time-wise? 15 minutes? 15? Okay, so I think it's all right. So some other realizations for detection, specifically detection of Majorana bound states in solid state physics, have tried to produce probes of Majorana using indirect probes, meaning that you're probing not the Majoranas or the candidate Majoranas themselves, but some ancillary system that's close to that putative Majorana. And so here I'm just citing some interesting papers that use these ideas of indirect probes. So for example, you can think of a quantum dot, which is connected with a nanowire with spin orbit coupling and the regular ingredients. And the idea is that if there will be a Majorana at the end of this nanowire, the quantum dot or the conductance through the quantum dot will be sensitive to this particle. And also indirect probes that rely on rings of quantum dots, which are this ring is pierced by a magnetic field, and then the persistent current which is formed due to the magnetic flux through the ring will also be sensitive to the presence of a nearby or a pair of nearby Majoranas in a one-dimensional realization. Okay? So these are very interesting, nice theoretical proposals, in my opinion. They rely on kind of basic, well understood physics. The problem is that they haven't been experimentally explored, and the experimentalists will claim all kinds of difficulties, magnetic field, for example, but also decoherence and other drawbacks, which allegedly would hinder this kind of experimental realizations of this kind of setups. So recently, a former student of myself, who's now a postdoc in Buffalo, and myself have proposed a very simple model, which is also inspired by this indirect probe of Majorana's idea. And in this model, we consider a Kitaev ring, which is just a Kitaev chain with natural periodic boundary conditions, and a Kitaev chain with open boundary conditions. And this, if this chain is in the topological regime, there will be a Majorana sitting here at this edge. There will also be a Majorana at the faraway edge, but I'm considering that this open chain is so long that only coupling between this edge and the Kitaev ring will be important. The Hamiltonian for such a system, and keep in mind there is no magnetic field involved in this proposal. And then this is the Hamiltonian, the ring Hamiltonian, which is just the Kitaev Hamiltonian. The Hamiltonian of this edge, which is not connected to the rest of the Kitaev chain, if it's in a disconnected Majorana from the rest of Kitaev chain, the Hamiltonian is just like this, just the Hamiltonian of one single particle, and the coupling Hamiltonian between this edge and the Kitaev ring. So, does this scheme would provide an unambiguous probe for an unambiguous Majorana signature? That's the question that I want to address. So, if this chain is in the topological regime, then this is the Hamiltonian. But if it's not, then this would be just a regular fermion trying to disguise as a low energy, or with an energy that it's so low that it's so close to zero that it cannot be easily distinguished from a zero energy real Majorana. But if this is the case, the Hamiltonian then is now replaced by this pieces here, right? So we are going to discuss both scenarios, and I am going to show you that these two different scenarios lead to very, very different signatures, in the sense that if you have this situation or this situation, the things that you're going to measure are going to be not quantitatively different, but qualitatively different. Okay, so just as a reference, let's look at the band structure. When the ring and the open chain are not coupled at all, so you have a zero coupling, so these yellow arrows here are just absent, and then you just have two bands which are related to the gamma plus and gamma minus Majoranas along the ring, and one band exactly at zero energy, which is the yellow band here, which is the band associated to the zero energy edge Majorana, which is decoupled from the ring. So just observe that this set of bands, they have time reversal symmetry, which means that they are symmetric with respect to k equals 0. They have chiral symmetry, which means symmetry of the bands with respect to zero energy. And as I mentioned, the band associated to this Majorana is exactly stuck at zero energy, as it should, if it's a zero energy Majorana sitting at the edge of this Kitaev chain. When I couple them, now, well, some things happen. Most importantly is that now time reversal symmetry is broken, is preserved, but chiral symmetry is broken, and this band, which is now hybridized with the ring Majorana's band, is shifted fully above or fully below zero energy, and for some choice of parameters, it actually touches the bands the hybridized bands from the ring. And this means that now you have some resonance energy between this yellow and blue or yellow and red bands. For this choice of parameter, it happens at 5 arbitrary units of energy, or -5. Okay, so it's interesting that if you tune some parameter in the model, these gap closing points in the Brillouin zone can move in some interesting way, but I don't have time to go go into this. So, but let's compare what happens is if I have a trivial fermion instead of a Majorana at the edge of this open chain. Now, first of all, there is not only one band at around zero energy, but two, because this fermion is 2 Majoranas. So you have 2 bands. And one of the bands, when there is non-zero coupling between this fermion and the Majoranas in the ring, one of the bands disperses very close to zero energy, never touching the hybridized bands from the ring, meaning that in this case, there is no resonance for choice of parameters which are consistent with the choice of parameters of the previous case. So there is very distinct difference between this scenario where you have this resonance and this scenario. If you just go on and compute the spectral functions using Gris function procedure, for the case where you have a Majorana state sitting here, you have spectral functions of the Majoranas in the ring and spectral function of the Majorana at this edge, and they look like this. And what's interesting is that the highest spectral weights of the ring Majoranas and of the edge Majoranas is exactly at 5 or -5, which is the resonance energy between these states, which means that there is a very high leakage probability between these states, that this Majorana can jump into the ring or vice versa, effectively leaving one unpaired Majorana in the ring. And also, now if you compare what happens in the spectral function, if you have Majorana versus trivial fermion, well, they actually look quite similar, except that they are very different qualitatively, in the sense that when you have here Majorana, which is connected with ring Majoranas, the spectral function of the ring Majoranas have very definite parities with respect to K and to momentum and energy, and this has to do with this commutator, whereas these parity relations are completely absent when the link or the binding is with a trivial fermion. You lose parity with respect to momentum and energy, and this has to do with this commutator. If you look at this spectral function, which here is a contour plot, color mapping of the spectral function, but if you look in three-dimensional plots, you clearly see this lack of K and energy parity in the spectral function. So there is an imbalance in K and energy and omega in the spectrum function when you turn on coupling between fermion and a ring of Majoranas. This directly translates into unbalance of occupation numbers, which is just the integral of the spectral function in energy. So if you look at the spectral function in the Majorana, when you have here a Majorana, you see that the plus and minus occupation number of the plus and minus Majoranas, first of all, they are the same. And this is not the case when you have coupling with a fermion, with a trivial fermion at the edge of this chain. So you see that there is a difference between the occupation numbers, which directly translates into this equality or difference between particle and whole occupation numbers in your chain. So that means that in this case, the occupation number of particle and holes is the same. And here the dashed line is just particle and hole occupation number when there is obviously no coupling. Then you have just the step function. It's either 1 or 0. But when you turn on the coupling, the occupation number is deformed. It's lower when it used to be 1, and it becomes a bit larger where it used to be 0. But the important point is that particle and holes have exactly the same occupation number, which is broken when these Majoranas are binding with a trivial fermion here, as you can see here very clearly. And this particle hole symmetry breaking is very distinctive signature that, well, distinguishes these two scenarios, and this leads to current, right? So when you have this imbalance in the occupation number of particle and holes, then this integral is just current, and you see that this is the current as a function of some of the model parameters. Same thing here, but as a function of another of the model parameter. And you see that when you have coupling with a trivial bound state versus Majorana bound state, in the case of Majorana bound state, there is 0 current, but when the coupling with a trivial bound state, you generate spontaneous current on your ring as a function of some coupling parameter between the ring and that edge state. And this is as a function of this two of the parameters of the Hamiltonian. So it happens regardless of the chosen parameters, the emergence of this spontaneous current. So these are the conclusions of this work, that these two scenarios are actually very, very different with respect to many aspects. Band structure, in this case, there is preservation of time and chiral time reversal and chiral symmetries, and whereas here you partially preserve chiros, only partially preserve chiral symmetry. The leakage probability between the states in the ring and this edge is high in this picture, but very low in the other picture. The spectral functions show very different parity properties in the two pictures. Occupation numbers are also very different in that in this picture, time reversal and particle hole symmetries are preserved but broken in the other picture. And therefore, currents vanish in currents along the ring. Spontaneous current along the ring, there is no magnetic field or bias applied. So spontaneous currents vanish in this picture, but there will be a spontaneous generation of current in this other picture. Which means that this very simple model does indeed provide unambiguous signatures of Majorana and could be used as a fundamental piece in a device aimed at detecting as being an unambiguous detector of a Majorana bound state. And with that, I come to my conclusions. I hope I have kept within the time. Thank you very much.
Hello. Thank you, Mariana. So for the questions, we have the following advantage at CIF. So since we have coffee break in the afternoon, we can ask all the questions during the coffee break, because the idea of this conference is to have talks of 40 minutes, and then if there is time left, we have questions here. Otherwise, we make all the questions and the discussions in the coffee break in the afternoon. So for Mariana, I believe the time is over. So all the questions can be discussed in the afternoon. So now we proceed with the second talk of this morning session. It will be given by Professor Eduardo Miranda from Unicamp. So please, Professor. And you have 40 minutes, so you choose. So you can take all the 40 minutes and questions in the afternoon with some food and some sparkling wine, or just leave some time for the questions now.
Hello.
Sounds like a better deal.
Of course.
Okay, how can you put this in presentation mode? Okay, thank you. I guess I can use the mouse, right? Or maybe, let me see. Okay, so first of all, let me thank the organizers for inviting me here. It's a pleasure to be back in Brasilia. I'm going to talk about transport properties of strongly correlated electron systems, somewhat related to the previous talk by Mariana. First of all, let me acknowledge some of my collaborators. The upper people are former students. Actually, this is a current student, Iago Godoy, Luis Felipe Faria, and João Getelina. And my more senior collaborators, Victor Quito from University of São Paulo in São Carlos, and José Abel Oils, also at São Carlos. The outline of my talk is I'm going to start talking about the problem of disordered electrons and why it's a challenging problem. Then I'm going to introduce a certain technique that is very powerful for analyzing disordered systems, so-called strong disorder renormalization group. And finally, I'll focus on the main topic, which is transport properties of these systems. So I'll start with a very old subject of Anderson localization. So Anderson introduced the idea back in 1958 that if you put disorder in a non-interacting system, so here you have a non-interacting system, you have a hopping element, and you have site energies, which are assumed to be random, independently chosen from site to site from a certain distribution that can be taken to be arbitrary at this point. So what Anderson showed, and it was confirmed by later work, of course, is that this band that comes out of this system, of this model, is such that you can classify the states into two types. The center states are going to be extended throughout the sample. So this is a computer simulation that shows the strength of the wave function, the square of the wave function throughout a lattice modeled by this model. And at the edges of the band, you have what we call localized states, states that do not extend throughout the lattice, but are localized in certain parts of the lattice. And these two types of states are separated by a mobility edge, such that if your chemical potential falls into the extended state region, you have a metal. If it falls in the localized state region, you have an insulator. And if you can somehow tune the chemical potential across this edge, you will have a metal insulator transition. And way back then, these doped semiconductor systems were investigated as models that might be well described by this kind of modeling that I showed. So you have a silicon wafer, and you have impurities. Phosphorus, boron are probably the most common. And depending on the concentration of these impurities, you might have a tuning across that mobility edge and a metal insulator transition. So actually, the experiments indeed show that there is a metal insulator transition in this system. So here it's the conductivity at 0 temperatures extrapolated to 0 temperatures as a function of the concentration of impurities. And indeed, the conductivity goes to 0 at a certain critical concentration. So you have what looks like a fairly conventional critical phenomenon. And so this conductivity goes to 0 with a certain exponent that, as you can see here, depending on whether it's an uncompensated or a compensated samples, this exponent is a half or 1. Now, unfortunately, we have by now extremely good numerical data based on And we have extremely good calculation for this critical exponent based on that model. And as you can see, this exponent has nothing to do with the data. Okay? So there's something going on here that's beyond the model that Anderson wrote down in 1958. And most people believe that what's lacking in that model is interactions. Okay? Now, another evidence comes from the following. As I said, localization is a very old problem. And so by now we know that, for instance, that the dimensionality is very important to the problem. Still talking about the model, the non-interacting model that Anderson wrote down. So in 1 and 2 dimensions, there is no transition between metal and insulator. All the states are localized, no matter how small the disorder of the system. Only in 3 dimensions do you have a transition between a metal and an insulator. Now, unfortunately for that picture, there's very good evidence of a metal-insulated transition in 2-dimensional systems. So this is data from MOSFETs, but there's also data from heterostructures where you can clearly see this fanning type of plot of here the resistivity as a function of the temperature as you change the concentration of impurities, and as you increase the impurities, you go from an insulator to a metal. Okay? But the theory says that for non-interacting electrons, there should be no transition in 2D. Okay? But if you now go and try to estimate, this is essentially silicon, so we know everything about the system. You can estimate the amount of kinetic energy and the amount of interactions in the system, and as you can see, the interaction energy is much larger than the kinetic energy. So this is a strongly interacting system. So once again, perhaps what's behind the discrepancy with non-interacting problem is the lack of taking into account strong interactions. There are other problems with the non-interacting picture. I'm not going to those details, but trust me, there are discrepancies between a description based on non-interacting electrons and the real systems. So this is what I call the disorder plus interaction problem. This is an old problem. There's a lot of work done on this. None of them can actually explain the discrepancies, I would say, consistently through all the data. So what I'm going to show you here is a very modest contribution to the problem, which is based on a few models that we can very reliably analyze using this so-called strong disorder renormalization group, or SDRG, as I will call it from now on. So first of all, I'm going to describe how the model works. It can be used in any dimensions, but it's only in 1 dimension that it becomes very powerful, because you can very accurately control the flow of the SDRG in 1 dimension. So the problem is best illustrated with the disordered Heisenberg chain. So just the Heisenberg model where the coupling constants are random constants distributed according to some distribution P of J. The only condition I'm going to impose at this point is that all the J's are positive, antiferromagnetic, and the distribution can be, in principle, anything as long as it has a high energy cutoff that I'm going to call omega. Now, how do I approach this problem? So the idea goes back to these gentlemen here, and it's the following. You take a certain realization of the disorder in a chain, and you look for the highest coupling in that chain. I'm going to call it omega because it's at the scale of the cutoff of the distribution omega. So this is a very strongly coupled pair of spins. If you look at just those 2 spins, the level structure is a low-lying singlet separated by omega from a high-lying triplet. And since this is a very high energy scale and I'm interested in low energies, I'm going to simply throw out that triplet. So you essentially replace the pair of spins by a strongly coupled singlet. But you not only do that, but you also do the following. You look at the neighboring spins of that strongly coupled pair, and you do perturbation theory and find that S1 and S4 once you eliminate this pair, they become connected by a renormalized coupling, a coupling that's given by second order perturbation theory, and whose value is given here. Now note the following. This coupling J tilde, it's smaller than both J1 and J3, and of course, smaller than omega. Omega is the highest energy cutoff. So the newly generated coupling is very small, generically. So the net result is that S2 and S3 disappear. Essentially, a singlet is something that's basically inert. And a new coupling appears between the neighboring spins, S1 and S4. And the topology of the infinite chain is preserved in one dimension. So now you iterate. You look for the next highest energy coupling, and you do the same thing, and you do it again and again and again. Okay? And then the distribution of coupling constants will flow. Okay? And the flow of the distribution is what I'm interested in. So pictorially, at one decimation step, you eliminate the coupling that's here, two couplings which are generically here, and you add a smaller coupling at this left end of the distribution. If you do this many times, unfortunately, there was an animation here that got lost going from PowerPoint to PDF. But what happens is that if you start with a distribution that's flat like this, it becomes increasingly concentrated in the low energy end of the distribution. It becomes increasingly divergent at close to J equal to 0. In fact, you can track the flow of the distribution, and you can show that it tends to this sort of power law distribution, but it's actually not really a power law because the power exponent is flowing as you decrease the cutoff. As you eliminate couplings on this end and become decreasing this cutoff, this alpha is going to 0. So this power law tends very slowly to a 1 over J distribution, which is not even renormalizable. Okay, so it's not even an allowable distribution. So, but it's never there. The alpha is never exactly 0, and it tends to 0 very slowly logarithmically. And many numerical analyses have shown that essentially all initial distributions tend to this very singular distribution as you crank up the SDRG, at least for this model. Other models are different. And what's important about this distribution is that it's effectively infinitely large, or tends to be infinitely large. How do we know that? We can, for instance, calculate the width of the distribution, the standard deviation of J divided by the mean, and it goes like 1 over the square root of alpha, and as alpha goes to 0, this goes to infinity. So the distribution becomes effectively, or the system becomes effectively infinitely disordered. Okay, so this is what allows us to do actual calculations in this model. And because it becomes infinitely broad and disordered, the method becomes also asymptotically exact. Why? Because remember, we did perturbation theory to second order, and if you look at the conditions for the validity of the second order perturbation theory, as the distribution becomes extremely broad, it becomes ever more exact, and it's asymptotically exact in the low energy limit. So, and then based on that, you can calculate various physical quantities, taking advantage of the fact that this is an infinitely disordered system. Okay, I'm not going to show how you calculate those systems, those quantities. It's actually not too hard, but for lack of time, I'm going just to rely on what I'm going to tell you. So, for instance, there are some systems that can be analyzed with this picture, systems that have a very one-dimensional character, and that are also disordered. And as you can see here, for instance, this is essentially the susceptibility as a function of temperature, and this, I forgot to put here, there is a prediction based on the SDRG for that quantity. It goes like 1 over T times log squared of T. And there is a reasonably good agreement between the data and the prediction. Of course, at lower temperatures, the system becomes aware that it's not one-dimensional, it's three-dimensional, and then this picture breaks down. Okay, so now let me get to the problem of transport. So one of the things that the method allows you to do is to calculate not only thermodynamic quantities like susceptibility, specific heat, and so on, but you can also calculate dynamical quantities, and in particular, you can look at the frequency-dependent conductivity of the system. Now here, we are still talking about spin, so we can reasonably ask what is the conductivity in the spin system. This is what we call a spin conductivity. So there is a conserved quantity. For instance, if you focus on this model, this XXZ model, which is in the limit where delta is equal to J, this is just the Heisenberg model, but you can also do this, allow this to be a different coupling constant. So this problem has a conserved quantity, which is the magnetization in the Z direction. This is a conserved quantity. And if it is a conserved quantity, you can associate with it a transport property. You plug it into one end and measure what comes on the other end, and this is basically the conductivity of the problem. You can do this for the spin density along Z. This is the current operator for the spin density. Basically, you transfer the spin density from side to side, and you can go on and calculate the spin conductivity based on, for instance, the Kubo formula for this spin current operator. Now, this was done using the SDRG, and what these gentlemen found was that the average conductivity of the system as omega goes to 0, this XSZ model here, goes to infinity. In other words, it looks like it's a metal, right? As omega goes to 0, you tend to the DC conductivity of this model, and this is a metal, which is strange. As I said before, for non-interacting systems, there is no transition in 1D. The system is always insulating. Okay? Now, this is saying that the system is metallic. Okay? So, this is a puzzle for the following reason. This model here can be mapped by this famous Jordan-Wigner transformation onto a spinless fermion model, which is this one here. So this model is equivalent to this model. So now we're talking about fermions, and conductivity is now a familiar concept. And in particular, if you put delta equal to 0, this is a non-interacting system, where you expect the system to be insulating for any amount of disorder. And this result here is valid even when delta is equal to 0. So there's a puzzle here. This result is telling you that the average spin conductivity goes to infinity, but the non-interacting model is known to be localized. Now, this is a special type of disordered model because the disorder here is in the hopping parameter. So localization is kind of anomalous in this problem, but it's well known to be localized. It's anomalous because it's not an exponentially decaying wave function, but it's an exponential of a square root of x kind of a wave function, but it's still localized. It goes to 0 as you go away from the center of the wave function. Okay? So if this is a localized system, how come we are getting a metallic conductivity? This was a puzzle. So the answer to this puzzle is the following. It's also well known in one dimension that the conductance, the DC conductance, has extremely large fluctuations. Okay, so in other words, for a disordered system, in principle, any quantity, physical quantity, is distributed according to some distribution. Now, if this distribution is extremely narrow, it's what we call a self-averaging quantity, then it doesn't matter that it's distributed. You can take, for instance, the average value to be a good measure of a certain physical quantity. Unfortunately, that's not the case for the conductance in one dimension, the DC conductance in one dimension. So in particular, you can define, you can look at the average conductance, and you can define what's called the typical conductance. There's many ways of defining a typical value of a certain random quantity. You can either take the most probable value, the median value, but here a very convenient quantity is to use the geometric average of that quantity. This is the definition of the geometric average. And you can, in this one-dimensional case, the average conductance is much, much, much larger than the typical value. Okay? What that means is that if you take a sample at random, most likely the conductance will be extremely small. It's going to be an insulator. But if you take an average over many samples, it's going to be very large because it's going to be dominated by a very few number of samples which have a very large conductance, but which are not representative of the actual problem you're dealing with. This is what this discrepancy between the typical and average value means. So we went ahead and we looked at the typical and the average. Actually, this is the distribution of the conductance. Remember that this conductance is a function of the frequency, and you have to look at it as the frequency goes to 0 to catch the DC limit. Now, as the frequency goes to 0, mind you, I'm going to use this quantity here, which is very convenient for this problem, which is the log of a certain scale divided by the frequency. So if the frequency goes to 0, this gamma value goes to infinity. Okay, so I'm going to always plot things with the gamma value here and look at the behavior of things as gamma increases. And as you see here, the distribution of sigma as gamma increases becomes broader and broader. So this is gamma equals to 0.8. It's much broader than this initial blue value here. So it's becoming very broad, consistent with this picture here. And if you look at the typical and the average value, they are very discrepant in this low frequency limit. Okay, so indeed, we using the SDRG, we confirmed the picture that was already known for the DC conductance of the system, and this shows that the average conductance that those people use is not the best tool to analyze the system. It's better to use either the distribution, which is hard, or the typical value. Now, this is the same, now looking only at the average and typical values, the average value can put into a universal curve if you rescale properly by square root of L, the average conductivity and the gamma value. For all sizes, they fall into a universal curve, and you can actually see the divergence, the log divergence with gamma that was found before. This log divergence here is this behavior here. So as gamma goes to infinity, this blows up, the conductivity goes up. It goes down because of finite size effect. If you increase the system, this high peak value goes to the right, as you can see from this rescaling here. So this is the average, the diverging average conductance that was shown before, but in the same region where the average conductance is going up, the typical conductance is going down as you increase the size of the system. Okay, so if you fix this value of omega here, for instance, the average conductance is telling you it's metallic, but the typical conductance is going to 0 as you increase the system size, showing that the typical value is telling you a different story. It's an insulating system. We checked for, as I said before, for delta equal to 0, the system is non-interacting, and you can do very large scale exact diagonalization computations. And the same picture emerges here with the exact diagonalization, and this is sort of a proof that the SDRG is doing a good job of the system. Okay, so we cleared up the problem, but there was no surprise in the sense that interactions did not drive the disordered system into a metal. This is what you would expect. The interesting idea is, can you find an interacting system such that the interactions can beat the disorder and make the system metallic and not insulator? So that's the idea. That's the question. So we went looking for such kind of system, and we found it. Or at least we found one example that could be treated with this reliable method. And the problem that we treated is very simple. It's the same old Heisenberg model, but now I allow for positive and negative coupling constants. So this problem had been analyzed before with the SDRG. And what's different here in this case is the following. Because J can be negative, when you analyze the strongly coupled pair of spins with a negative constants, in this case, the triplet is going to be the ground state and the singlet is going to be the highest energy state. If you eliminate the singlet, you're left with 3 states. 3 states is equivalent to a spin 1 degree of freedom. So in other words, you replace a strongly coupled pair when J2 is negative by a new effective spin 1. And you can do this and iterate the model, and what comes out of this analysis is that the size of the spins begins to grow, and it grows without bounds. You start generating spin 3 halves, spin 2, spin 3, spin 4, and so on. Still, it can be analyzed. You can be accurately analyzed with the SDRG. And I call your attention to the following. Using the same Jordan-Wigner mapping that I talked about before, you can show that this system is equivalent to this spinless fermion model, where you have a hopping term and you have interactions which are both attractive and repulsive. Okay? So although I'm writing it in the spin language, you can also think of it as a spinless fermion model with both attraction and repulsion. And what comes out of the analysis using the SDRG, okay, this is a very long story, I'm giving you the results, is the following. First of all, the average conductivity is indeed metallic. In other words, as it's not a log anymore, but as omega goes to 0, the average conductivity diverges, okay? But once again, you have to look also at typical values to see if the average value is not fooling you. And if you look at the typical value, and it's shown here in the green, blue, and orange curves, it also goes up as the average value. And it goes down, as I said before, because of finite size effect. As you increase the system size, actually you can see it here. As you increase the system size, the region where it's going up becomes larger and larger, and it only goes down when it reaches a certain value where the system starts to realize that it's actually a finite size system. So in this case, both average and typical values are diverging as omega goes to 0. This is truly a truly metallic system, disordered metallic system in one dimension, where you can drive, you can beat localization with interactions. But remember, positive and negative interactions, attraction and repulsion. You can look at the distribution. It's seen here as gamma increases. The distribution, unlike the previous case, it becomes broader, but it's not, in the previous case, it became broader, but it sort of invaded the small region of sigma. But here it's becoming broader, but it's actually moving to the right, moving to the side of very large sigma values, in other words, metallic values. So it's very different from the previous system. So this is a truly metallic system in 1D. So finally, I don't know how I'm with time, but if there's still time, I can answer questions. My conclusions are that the disorder interaction electronic systems are still an open problem. Of course, everything that I talked about from my side was one-dimensional. It will be interesting to try to go to higher dimensions. But I argue that this is a very difficult and challenging problem where insights from a very reliable method are truly valuable. And this is what the SDRG brings to the problem. I also emphasize how important it is, especially in one dimension, to look at distributions, to look at typical values as opposed to average values. And we found at least one model where you have metallic behavior in 1D, where interactions beat localization. Okay, and of course, the biggest challenge is to go to higher D. Okay, I can talk about why it's hard to go to higher D, but anyway, that's what I wanted to tell you about today. Thank you.
I believe we have time for a question.
Eduardo, thank you for this very interesting talk. And towards the end of your talk, you mentioned that you found at least one, and we know that one is sufficient for a proof of concept, a model in which you achieve metallic behavior in one dimension, but it relies on antiferromagnetic and ferromagnetic spin correlations being distributed randomly in the fermionic picture. That would mean attractive and repulsive interactions between these fermions being distributed randomly.
Right.
How can you achieve such a
Okay.
system in a material?
Okay, so of course, as you said, this is at this point a proof of concept. Try to show that there is at least one model where it can beat localization. I call your attention to the fact that attraction beating localization is not a surprise in a sense, because if you start with a purely attractive system, this is a superconductor, and there is a range of disorder where disorder is irrelevant, the superconductor survives, right? But here it's a mixture, first of all. If you put only negative J's, it doesn't work. It's a different problem, okay? It's a true superconductor. So this is not a true superconductor in the sense that it's randomly plus or minus. The random problem with negative J is a different problem, it's different universality class. It is a true ferromagnet. This is not a ferromagnet. Now, coming to the question of specific experimental realizations, there is one way, which is the following. There's a class of ions. I think beryllium is one example, but I think there are others, where there's this phenomenon called charge disproportionation, which means the following. If you look at the energies of the ions, of a sequence of ions, a sequence of valencies, so if we put 1 or 2 or 3 electrons, there are a few elements where when you put 2, it goes down. Usually you put 2, it goes up, but for a few elements, it goes down. And this has been modeled in the literature as what are called negative use centers. Okay, so these are models with local attraction in the particular sites where you have these particular elements. I know that beryllium is one of them. I forgot. There's another example too. So if you dope a system with negative use centers, you might realize a random plus J, negative J system, because the other atoms might be positive J, and this would be a negative J system, or an attraction and repulsion. But this is just a proposal. Of course, you have to see if you can grow it, and this is 1D, and so on. But just to say that this is not completely crazy. There are ways of at least trying to realize this kind of physics described by this model.
Thank you.
Any other question? Or we postpone for the afternoon session with some sparkling wines?
I'll be happy to answer any questions.
Okay, so then let's thank the speaker again. And now, just in a few seconds, we'll have the next talk by Professor Demetrio Antonio from University of Brasilia. Just give me 10 seconds so I can put the presentation here on the computer.
and new materials, new organic semiconductors. I will share a little bit of what I have been doing at the University of Arizona, Georgia Tech, and at the University of Cergy-Pontoise in France, to try to introduce you to these new materials, organic materials. So first, I thought this presentation for my students. Hopefully, some of them are here and others are following us on the internet. So you see, I decided to avoid adding too many questions, trying to motivate not only them but others to join our research group. So I would discuss a little bit of the differences between organic and inorganic semiconductors, the research we have carried out in the US and in France, and now the topic of my current research, which is to try to use artificial intelligence in the design of these new materials. So just to give you a quick review of what are the differences between organic and inorganic semiconductors. When we think about inorganic semiconductors, we think about silicon. Basically, all our modern electronics are based on this material. When you talk about organic semiconductors, it's essentially molecules of polymers. So the idea is that in silicon, it's not there for a long time. If you think about 1953 as the first transition-based computer, it's less than 100 years ago. When I was at Georgia Tech, we bought a Dell computer to run our simulations, and the person who was there installing this new cluster, he said he was there to install the first computer that Georgia Tech ever bought in the 50s. So it's not so long ago that we had our first modern computer. But when you think about inorganic semiconductors, you're basically limited to these blue elements in the periodic table, and there are around 150 compounds that have been characterized as inorganic semiconductors. So it's not a very large amount of different systems. No? Modern electronics is based in silicon. It's a market that's always growing. We have heard, for example, after the pandemics that there are some shortage of semiconductors, and even cars could not be finished being produced because the absence of semiconductors. It's a market that's predicted as $600 billion for this 2024, and this means a growth of 20% compared to last year. And it's always generating innovation in health, safety, energy, basic research, and lots of other technologies that are around us, as we all know. But there is always room for new technologies. And when we are talking about new technologies, we're thinking about hybrids, so technologies that are using semiconductors, inorganic, and other things like organic semiconductors. So when you think about applications of silicon, you can go from glass to iron, steel. And what's interesting is it's essentially a very abundant material. So it's sand, no? But you need a lot of money to transform it into monocrystalline silicon, which is really the expensive one that makes our computer processors. So basically, you have 3 degrees of purity from the most pure, which is electronic grade silicon, to the not so pure, like the metallurgical grade silicon. In metallurgical grade silicon, we produce here in Brazil, and we stop there. These other 2 are just somewhere else. So in metallurgic, it's 98 to 99% pure. Solar grade, which is used for solar panels, you have 5 nines to 6 nines. And the electronic grade is 9 nines. So only companies in Asia can produce electronic grade silicon. And it's an industry that is essentially out of reach for our country, basically. You know? It's very expensive. With respect to solar cells, We know solar energy is the most abundant source of clean energy, and it has the lowest impact on the environment. I put between quotes because, you know, there is an impact to make the panel. Once the panel is done, okay, it's not a big impact on the environment, but to make the panel, there is always an impact. There is always improvement in the efficiency, as you see, and currently this is a clean energy that has the price almost comparable to energy coming from fossil fuels. So we discussed now, for example, about using solar energy to make hydrogen using inverse electrolysis and then use a fuel cell to generate electricity again, because it's cheap to have solar energy. No? There are some drawbacks in the silicon technology, which is the panel needs to be thick. So when we study solid state, we know that this is an indirect gap material, so you need the photon to travel a little bit in the electron to find a photon and then generate a whole electron pair. So the panels, they need to be thick. And also, only part of the electronic spectra or the solar spectra is absorbed in these kind of panels. And besides, very few countries can produce solar panels. Brazil is probably not one of them. Here I brought this picture to illustrate how the inorganic semiconductors, the inorganic semiconductors evolved and are still bringing innovation in our daily life. So here's, for example, the evolution of our light bulb. No one here probably used a candle to illuminate, but the ones with gray hair knows very well the incandescent lamp. Probably there is only one in the synchrotron now generating the electrons, right? I remember that they generate all that physics by an incandescent lamp that's there as a source of electrons. We moved to the fluorescent lamp, and now we are in the LED lamp. In the beginning, this LED lamp was just terrible. Those who work with architectures and etc. used to say that this is a terrible light for our environment because you essentially have white light as a combination of red, green, and blue, very sharp peaks. So we are used to this beautiful and broad light from the sun, and we replace that by these three peaks. But then comes the innovation in the semiconductor industry. Nowadays, there is an RGB, some called LD motive technology that essentially reproduce the entire solar spectrum. So forget about the old LEDs, now you have solar spectrum. So what about the inorganic semiconductor? So the first molecule that was studied with some interesting phenomena of electroluminescence was this molecule anthracene. Don't know if you remember from your organic chemistry, it's basically 3 fused rings. In the past, we had naphthalene at home in the closet of our grandma, right? The small pellets of naphthalene. This is the next one, anthracene. So anthracene was discovered to be photoconductive in the 10s. But then it was really in the 60s that the intense research on this material started. And they started to be investigated and discovered. In the 70s, they discovered that organic polymers could be doped and then transformed into semiconductors. And this discovery led the Nobel Prize in Chemistry in the 2000. So here are the 3 gentlemen that won the Nobel Prize. The Hideki Shirakawa and Matt Darmin, they are already deceased. The only that is still living is Alan Heeger. Keep this name in your head, Alan Heeger. So LEDs. So one of the applications of organic semiconductors are the light-emitting diodes. The first light-emitting diode, commercial light-emitting diode, came in this Philips shaver in the 2000, was displayed in some James Bond movie. My former professor, supervisor, he always carried this shaver everywhere to show, oh, this is an LED. Nowadays, he doesn't carry it anymore because everybody has a cell phone with an OLED display on it. So it's just common technology. Nowadays, we have cell phones, we have foldable phones. That was initially an idea of having LEDs, organic material, polymers, because they are foldable. You could fold it, and we have nowadays a cell phone that has a screen that's foldable, and televisions based on organic LEDs. They are also have been used to produce light, so they are called the OLEDs, the white LEDs. And the idea is that you can produce light from a panel that is two-dimensional. So the idea is you could, just do several forms and shapes and interesting lamps where light comes from the entire surface. This didn't went quite well, but hopefully in the near future you have some lamp like that at home. So now you have a panorama of all organic and inorganic semiconductors, solar cells and solar panels. And this figure is quite interesting because you can see there are some technologies that are very high up in efficiency, and some technologies that the evolution throughout the years were almost flat. So you don't see much increase, but they are increasing slowly as a function of time. Of course, those multi-junction cells, they are quite expensive. They are basically in the satellites where it's interesting to pay the price of a 47% efficient solar cell. We basically have, if someone has at home a solar panel, it's basically in the blue technology, the crystalline silicon cell. But here in this orange corner, we have the organic cells and one that's a strong competitor, the perovskite cell. So the perovskite is quite interesting because of these sharp rays that you can see here. It's the quickest rays in efficiency that was ever observed in this entire chart. So it went up quite fast. Now they are trying to solve some problems, some stability issues, the fact that these perovskites, they have lead, so this is not very good for the environment and things like that. If you look at the organic cells, they go up also quite slow. They reached 14%, and then there was a small jump from 14 to 17. This increased the energy of the community to try to find new molecules. And so people are still think that organic cells are in the game. Why organic cells are so interesting? Basically because it brings innovation to the energy production. So the idea is you can make panels that are transparent. So for example, if you see, this is the roof of a shopping mall in Bahia, where you have the roof that's allowing light to go through, but also you have energy production. You can have the leaves of some artificial tree where actually they are solar panels. And also you can produce them in a roll-to-roll fashion. So for example, I was recently in Denmark. They had a machine that in the beginning was thought to produce capacitors, but they had this idea of roll-to-roll production and deposition of different layers and etc. So the University of Southern Denmark got this machine from a company they gave to the university, and they are now producing solar panels in a roll-to-roll fashion. So this is the idea of making high quantity, cheap panels, and not so high in efficiency, but maybe the price will help to the market to grow. So basically this was the introduction, and the idea now is to discuss a little bit of what is our job, trying to do theory and understand what's going on. This was a cartoon picture that myself and another PhD student, we played. Of course, this has nothing to do with the reality, but the idea here is to illustrate a organic transistor. So you have here silicon dioxide as a gate, the two gold terminals, some organic molecules in between, and then the electrons jumping from one molecule to the other. So in the beginning, we had to use the ideas of inorganic semiconductors, band transport, look at the effective mass, and etc. But we quickly realized that charge transport happens in organic semiconductors in a completely different way. And we started to use the idea of Marcus equation. So I had the honor to meet Rudolf Marcus, a Nobel Prize in Chemistry in '56. He was the one who described for the first time electron transport in proteins. So the idea was you have a protein here, a protein there, delta G, an electron jumps from one side to another. So we said, well, maybe this is the way we have to describe the charge transport between organic molecules. So when I arrived in the States, while I was still a PhD student at the University of Campinas, we used this equation to find the rate of charge transport. And in this equation, you have two parameters, which are the electronic coupling and the reorganization energy. So the electronic coupling basically tells how one molecule couples electronically to the other. So if the molecules are far, the electronic coupling is small. If the molecules are close, it's bigger. But there is one point. Here you have quantum interference. So if the molecules are very close, but the phase of the orbitals are not correct, this coupling can be small as well. The organization energy is another parameter that basically tells how big is the change of a molecule when the electron goes out or when an electron comes in. So usually these molecules change drastically in the structure as it gets charged or it releases a charge. You can have, for example, an electric field, and then delta G will enter as the difference between the potential energy surfaces of the two molecules, right? So our first paper, it's a paper that I was honored to be there because it was communicated at PNAS by Alan Heger, the Nobel Prize. And the idea was to shed light for the first time in how you can compute these electronic couplings in a very simple way and try to understand a little bit better how transport between molecules happens. And then after that, I finished my PhD. I came back to the States, now at Georgia Tech, and I was able to participate into a program, a material science program, in which we kind of learned the way to do science in this business. And the idea was essentially by doing this circle, this virtuous circle of theory, synthesis, and characterization. So you could discuss with the organic chemists about different molecules, possible molecules they had in mind. They always have hundreds of molecules in mind, but of course it's difficult to synthesize all of them. So we can do some theory in between to figure out at least a priority list, let's say. And then someone goes there, make the devices, test, and see if it works or not. So this was an interesting way of doing things that I'm doing until today. So in 2007, we published this paper. It's also a quite interesting paper. It's the most cited papers of everyone here except the boss, Jean-Luc Breda, that he has a paper with almost 10,000 citations. So this one has only 5,000, but it's a interesting, important paper where we basically laid down the theory behind charge transport. It's a review about all the theories at that time. And then here is an interesting picture that I showed to the students. Professor Jean-Luc Breda, he was the mentor of all of these people. We have Spanish people, Russian, Moldavian, myself from Brazil, Chad from the US, Georgie from Lithuania, France, and Egbert from Austria. So we have people from all over the world trying to work on the theory of organic materials. After spending quite some time in the States, I shifted my geometrical point to France after discovering a collaborator, Georgie. And then we moved to this interaction between the University of Sergipe-Pontoise and in Brasilia. And we start to use other approaches and do some other systems. So here's one example of the two approaches that we can use to characterize these organic materials. So these are two organic molecules. You know very well the fullerene, the buckball. This is another organic molecule. And the idea is if you put these two molecules together and you shine light, you have electron and hole pairs. And everything happens at the interface. So how can you simulate the interface? One way is really put all these molecules in a big box and use molecular dynamics to prepare this interface and then analyze the interaction between the molecules. So this is one approach that we can do. You can imagine that you need powerful machines to compute all these equations, all these interactions, and etc. And this is why we heavily use computers in our simulations. But there is this material, especially was the cover of an important journal in our field in 2014, the description of this interface. But then you can have another approach for those who like more equations and models and etc., which is also quite interesting. And this was the work of my former PhD student, Leonardo Souza, Vyacheslav Koropsheno, the Russian Moldavian in that picture, and Georgesini. And the idea was the following. So we know when you put all these molecules together, different molecules, at the interface, there are some strange things happening. So for example, the orbitals of these molecules, they kind of bend. So this is what we call the band bending. Another point is, for example, so here you can see this bending, and in this model you can tune this band bending. So this is one of the ideas. In the molecules, when you have molecules, you create an interface, there is a band bending there, and that's it. It depends on the molecules. If you make a model, you can have this as a parameter, and you can change the parameter and see how this band bending influences the electronic separation. So the idea here is at the interface, you have light being transformed into a hole and an electron. The idea is that these electrons and the holes will separate, will generate a current. And of course, we want the more electrons to separate, the higher the efficiency of the panel. So we want to learn how this band bending influences this separation. Another thing that Eduardo mentioned was for example, the energetic disorder. So these molecules, as you could see from the previous picture, they're all disordered at the interface. So they have different environments, the energy levels, they are in a distribution, and how these disorder influence this charge separation. So in this paper that we published some time ago, we used Monte Carlo simulation to find out what's going on. So we created the interface, we have the sites, we generate excitons, we see how they migrate and how these excitons break with these two parameters, band bending and disorder. And here's just a picture to summarize, to show you what we are looking for. So we have different band bendings, different disorder, and the survival rate, which is the higher the better. No? So you see, to have a high survival rate, we need an energy bending of around 0.3 electron volts, and this sigma, the disordered, it basically doesn't matter. So these are the types of numbers or insights that we are looking at. So this was also a cover of another advanced theory and simulations. The idea here is to represent the sites, as I mentioned before, the light shining and you generating electricity. So this is important to organic photovoltaics. Now we are going into another field which is trying to use artificial intelligence to discover these molecules. So everybody knows that artificial intelligence is making a big buzz around all the areas. In 2023, it was the birth of ChatGPT. Lots of people are kind of do not like ChatGPT. It speaks quite crazy things and etc. But the real fact is the application of artificial intelligence is definitively helping the design of new materials. So, for example, there was a Nature paper recently by Google company and another laboratory who put together a lab with only machines working, kind of making synthesis and etc. And the system, of course, coordinated by artificial intelligence, and they could generate new materials and things like that. So, for example, when I saw your superconductors, I always think about these X and the Y's in all these crazy formulas. Is it possible that artificial intelligence can be used to design the proportions? Because I think it's a quite complex problem, no, to play with the quantities and etc. So the idea is, we had, for those who lived already quite a bit, probably you've seen that AI, artificial intelligence, came back and forth many times. So every time there was a wave, then the wave disappeared, and they came back again, and etc. But I believe this time the wave, artificial intelligence, is here to stay. And the idea, the basic reason is the convergence of all of that, big data and computers. So we have now data coming, lots of data coming from everywhere, and we have machines to process that. So that is the big difference. So I think this time we have to take it seriously and try to figure out how can we use artificial intelligence to design new materials. So our projects in the group now, they are going in two directions. The first direction is how can we use artificial intelligence to compute relevant properties in organic molecules. So of course the dream, someone who is selling something on artificial intelligence will show you this picture. So you give me the molecule, I don't need to do any calculation, now you give you the spectra right away. So this is the dream. Of course, we are far from that. At the moment, we are thinking about, for example, there are some calculations that we have to run, a very large number of calculations that we know they are very similar. At the end, they not contribute very much to the result, but we cannot select them. We don't know how to select which are necessary, which are not. So what we do, we compute everything, and we spend lots of hours computing doing these calculations to get a spectrum like that. So the idea is to use artificial intelligence to select which are the geometries, the different conformations that will contribute to the property that we are looking at. So these molecules, these organic molecules, are very flexible. So if you take only one sample of the molecule and run a calculation, this is really far from what we have in nature. In nature, you have a combination of thousands, millions of conformations. So the idea is we generate quite easily those millions of conformations, but we know only a fraction of those, they contribute to the spectra, for example. How can we select this conformation? So this is one of the ways we plan to use artificial intelligence. So here's one example for a solid, and the idea is the possibility of creating new materials. So you use, for example, machine learning to learn a kind of a solid that you already know, what are the properties, and you train these, you give some information on the electronic structure, you give some information on the geometrical part, and you teach the algorithm what is the property. And then at a certain point, you come up with a system that it's not even synthesized, and the software will give you the property. So this is what people are predicting that will happen in the near future. Again, this is more for molecules, but again, you need to teach the computer what is a molecule, and then you give another molecule, it learns what the molecule will be or what are the properties. No? The other area that we are trying to explore is the design of new organic molecules. So as I mentioned, if you ask organic chemists to give you a group of molecules that they think is interesting, they can give you 1,000 molecules quickly, no problem. But it's difficult for us to compute 1,000 molecules. No? So the idea is we can compute a smaller number of molecules, and you give the artificial intelligence algorithm a fraction of them. And they try to learn what are the properties of these molecules. And then we ask, now, if I take this fluor atom, instead of here, I put it there, what is the property? Is it closer to what I think it is? And we have the aid of artificial intelligence algorithms in this design of these molecules. I particularly liked this picture. This was created by artificial intelligence. And the idea is, the point why these algorithms may work, the idea is this space is multidimensional. It's impossible for us to combine all the different properties and try to look at a specific direction that will maximize or minimize what we want. So the idea is only a computer can, with algorithms, of course, can try to minimize and maximize several variables at the same time and give you a trade-off between all of them. So that is the idea. Okay, now we reach the conclusions. So inorganic semiconductors are, and they will be for a long time, the main actors in microelectronics. But organic semiconductors, they are here to bring innovation and performance in some aspects. So for example, in the past, organic screens, they were way worse than what we had at the time. For example, LCD screens. Nowadays, organic LEDs are the first, the top-notch organic panels, display panels. No? So there are some areas that nowadays organic semiconductors already dominate, let's say, the market. There is still much research in order to make electronic devices based on organic semiconductors, cheaper and high efficiency, with higher efficiency and durability. And we believe that the flexibility that carbon chemistry gives us, it can be combined with artificial intelligence to generate significant innovations in electronics. So the problem we have here is essentially to the problem of the pharmacy industry, for example. Create new drugs for treating new diseases is basically the same thing. And of course, they are investing a lot of money in this direction as well. Okay, with that, I thank the University of Brasilia, the financing institutions, and I thank you for your kind attention.
Thank you, Demetrio, for a very nice presentation. And I think we have a few minutes for questions, if there are any questions. I think I have one simple one. So, is it easy to start using the algorithm for artificial intelligence, or it takes a few years to learn how to enter the area?
That's a wonderful question, Alexander, because what we have done, we started to try to figure out a book, a course, whatever, and we found a student of ours that he was abducted by a bank. And this bank, Itaú Bank, what they did was to put together a course of artificial intelligence with professors of ITA, UNESP, and things like that. And the idea was to prepare a team of young scientists to apply artificial intelligence in the bank. So they trained these people, they hired these people, and they are developing AI in the bank. But then the professors, after the course, they realized, wow, we really did a good job preparing this course. So they put together a book. This book is very expensive. It costs like 500 reais, but it's free in our library, the electronic version. So when I saw that, I said, well, that's it. That's where we are going to start learning artificial intelligence. So we started with a small team of students, and what was interesting is I sent to all the students in our postgraduate. Anyone wants to learn artificial intelligence, come with us. We will study this book. And I have students from gravitation that are studying gravitational waves. I have students that had already another area decided, but they want to learn artificial intelligence. So artificial intelligence is really the first time I have students asking me, look, I want to work with you, but with artificial intelligence, not with something else. It's something that has to do with artificial intelligence. Because the problems are really transferable, you know. If today you learn how to design an organic semiconductor, tomorrow you will be at Ashe, design a new drug, making a big salary. So the idea of, you know, using this knowledge. One of our students, he tried really hard to stay in France. He was in the Center for Artificial Intelligence in Marseille. And at the end, he couldn't find a permanent position. He is working now at SNCF, so it's the train company of France, using artificial intelligence to predict how many trains they need to move people and etc. So that's the idea, which I think attract quite a bit the students to learn this tool. For us, it's a tool, but I think it's a quite powerful tool.
Okay, Ismael, just the last question.
Demetrius, thank you for the very nice talk. I would like to know, we know that there is several technologies on AIs, for example, there's ChatGPT, and there is others who produce images. Is there one that's already able to process these organic compounds that you have mentioned?
I just reviewed a proposal for the FAPES, which Espírito Santo, of a professor in Vitoria, and he's developing his own codes. So I think at the time, what I know at this time is, for example, there is one big company that has developed a force field that uses artificial intelligence to parameterize the force field. So in the past, parameterization of force field was like a life of a scientist. So I met one day a lady called Sally Price from England, and her life was parameterized force fields. And I said, wow, I found you, great, I have a molecule. What are the atoms? Oh, I have carbon, hydrogen, and sulfur. Oh, sulfur I didn't parameterize yet. Okay, bye. So that was the idea in the past. No? Nowadays, you give a molecule to the computer code, it figures out what are the atoms. If there are no parameters, it uses artificial intelligence and some algorithms and generate the parameterization, and that's it. So, and this is commercial right now. But regarding these softwares for other things, like there are a few initiatives. So, for example, the University of Marseille, it put together a center for artificial intelligence. It hired a Brazilian professor, Mario Barbati, but he's there in Europe for a long time, and he's working on artificial intelligence, developing these codes. So I think now it's more in the academics, and of course, probably in big companies somewhere, there is some scientist in the basement doing some programs that we don't know, but they are coming together. No?
Thank you.
No.
Okay, so let's thank the Metro again.
Thank you.
And we'll be back at 2 p.m. for the afternoon session of the workshop. See you all then.